Hello, everyone, and welcome to Lab Manager's How It Works webinar series. My name is Sarah Kirsch, and I'll be moderating this discussion, a very dry webinar, Desiccants used in elemental analysis by combustion. We like our webinars to be very interactive, so we encourage you to submit your questions to us at any point during the webinar. Our speaker will address these questions during the question and answer session following his presentation. To ask a question or leave a comment, simply type your query into the Q&A box located on the right-hand side of your screen. We'll try to address as many questions as possible during our time together. If we happen to run out of time, I will forward any unanswered questions to our speaker and he can respond to you directly if possible. I would like to remind you that the webinar recording will be available on demand shortly following this presentation. So please watch for an email from Lab Manager on how to access this free video once it's available. I'd also like to invite you to visit the handout section for more information about this presentation. Finally, I'd like to extend a special thank you to our sponsor, EA Consumables. Their support allows Lab Manager to keep these webinars free of charge for our readers. With that, I would like to introduce our presenter for this webinar. Scott Hughes has a long and storied career in the field of elemental analysis. He founded EA Consumables, the exclusive U.S. dealer for Elemental Microanalysis Limited, in 2013. Prior to that, he founded Elementar Americas and served as president for nearly 15 years. Scott has also been president of Lexay Inc. and vice president of Varlant Instruments. Additionally, he spent 9 years with UIC Inc. as Senior Vice President. As a known authority on organic elemental analysis, Scott is regularly asked to speak at conferences. Scott holds a BS in Chemistry and Physics from Beloit College and a PhD in Analytical Chemistry from Iowa State University, as well as an MBA from the University of Chicago. Scott, thanks for joining us today.
Okay, so thank you for attending a very dry webinar, Desiccants used in elemental analysis. Okay, elemental analyzers are commonly used in the measurement of the concentration of one or more of elements, carbon, hydrogen, nitrogen, and or sulfur in a wide range of materials. Desiccants are used in elemental analyzers to separate or remove water, which may be present in the original sample or formed during combustion. This webinar will discuss the different types of desiccants which are used and their relative benefits and limitations. So in 1923, the Nobel Prize for Chemistry was awarded to Fritz Pregel for his development of a carbon, hydrogen, nitrogen analyzer. So this analyzer was designed to combust from 2 to 4 milligrams of organic samples in the presence of oxygen, converting the sample's carbon to CO2, nitrogen to N2, hydrogen to H2O. In the ensuing 100 years since that time, there have been a great number of improvements in detectors, electronics, and automation. However, the basic principles and chemistry of the technique have not significantly changed. Samples are still combusted at a high temperature, around 1,000 degrees Celsius, in the presence of oxygen. Combustion gases are passed over reagents to quantitatively convert the analytes of interest into a single molecular form. And shown here are some of the current models of elemental analyzers that are typically in use today. So I'm showing right now two popular combustion tube filling systems. The one on the left is the Thermo Carla Urba or Costech type of system, and the one on the right is the Elementar type of system. Elementar introduces oxygen through a lance directed into the middle of the tube. And if I get this to work right, that's showing the oxygen down, the sample falls, high temperature with the oxygen, and you get a combustion. The Carla Urba system puts in a plug of oxygen. Come on. Oh, it's just not working. There we go. Plug of oxygen and times the sample to drop where the oxygen and the sample get there at the same time. The exothermic reaction of the tin container with the oxygen results in a very high temperature approaching 1700 degrees. Okay, so we have the initial combustion. Drops in, adds oxygen at 1,000 degrees, and then this produces a soup of combustion products, several forms of carbon, several forms of nitrogen, a couple forms of sulfur, water, halogens, and your excess oxygen from the combustion. Next, either this exothermic reaction heating with the tin, and or in some analyzers they do use a second furnace afterburner, will convert this carbonate, the CO3, over to CO2 from the soup. Next, the gases pass over a oxidation agent, copper oxide or chromium oxide are typical ones used. That will bring the carbon monoxide that may have formed up to CO2. Our goal here again is to get all the carbon into one form, all nitrogen into one form, all sulfur into one form, etc., so we can quantitate them. And then if we're doing carbon nitrogen only analysis, the sulfur needs to be removed. This is usually absorbed onto either silver cobaltic oxide or a plug of silver wool. Historically, lead chromate was used, which is extremely effective. However, due to the toxicity of the lead chromate, that's not used anymore. So remaining are these elements here. Now this is time to go into the reduction process. So we have the CO2, which is our final form of carbon. That's what we want. We do have N2 and nitrogen oxide. So in order to get that all into the form of N2, we pass these gases over copper at about 500 to 650 degrees Celsius. This will convert the NOx's over to N2. It will also absorb the excess oxygen that's in the analysis. Now, we also may have SO2 and SO3 available. So these will also be absorbed if we're at 500 to 600 degrees Celsius, but not if the copper is at a higher temperature. So in the case where you're also looking to quantitate sulfur, we would just increase the temperature of that reduction tube to 850 degrees. That will still reduce the SO3 to SO2, but not absorb it. Now, the copper that's used in this reaction, it's a surface area reaction, so there are different forms that are available. There are granular ones, wire ones, fine granulars, coarse wires, etc. And so fine and all will have different properties that with back pressure, etc. And your manufacturer of the analyzer will probably recommend one form versus the other. And we still have the leftovers of CO2, N2, H2O, and possibly SO2, depending on the temperatures there. So the next step is to separate these analyte gases. They're all in one form. That's what we're looking to do. And generally, the most common methods of separation for the analyte gases is chromatography, either isothermally or by temperature ramping. The general challenge is to separate the N2 peak from the CO2 peak, and at the same time, not to have the H2O vapor peak or the SO2 peak be too long coming out of the column, which then tends to make them low and broad, which is more difficult to quantitate. You can improve upon the situation utilizing a ramped temperature or separation. In this case, you get a much better separation between N2 CO2 while still bringing H2O and SO2 out in a reasonable time and with sharper peaks. So a question is, do you need hydrogen concentration? Hydrogen concentration is very important for some applications. Organic samples for compositional purity determinations, often used in the pharmaceutical industry, is key. Also, hydrogen content is important for the ultimate analysis of coal. It is used directly to calculate the heat of combustion, which obviously is very key for coal. But the vast majority of elemental determinations are concerned with nitrogen, carbon, and or sulfur only, and the hydrogen is not required. And in general, elemental analyzer life is easier without hydrogen. You know, if you wanted to measure hydrogen and do it in a meaningful way, you have to first dry the sample free of absorbed moisture, and then the issue is the other things that you're measuring, the carbon, nitrogen, would not be then on an as-received basis. You'd have to calculate it back in again. So if you were not needing to analyze hydrogen, if we can just remove it prior to the determination, it makes things easier. Higher efficiency GC packing can be used to separate the larger concentrations of N2 and SO2 without greatly extending the analysis time. So there are also another class of analyzers in elemental analysis, which are called macro-elemental analyzers. Mainly, we want to analyze a larger sample due to overcome homogeneity issues. How much sample should you use? The old adage is as small as possible, but as large as required, which, you know, is kind of confusing. Less sample means less time of analysis, less reagents used in the analyzer, and for some samples, too small a sample size, though, can lead to very non-representative results. A classical example of this was if you have to analyze the nitrogen content or carbon nitrogen content in Raisin Bran. You know, a 2 milligram sample of this could be very different whether you're grabbing the raisin or the flake. Feathers are similarly very inhomogeneous. The tips of the feather versus the stem, etc. Soil analysis, that's very important in the agricultural industry. Again, soil can be very different from 1 foot to another foot over. Taking a larger sample size helps. One way of getting rid of homogeneity effects is to grind the sample. There's several different types of grinders. However, this is also limited. It can change the nature of the sample. Some things grind better than others. Soil grinds pretty well. The flowers and feathers and Raisin Bran are less easily ground. So size is a factor. Often analyzers use the larger sample size of 200 to even 1,000 milligrams. So soy meal is a typical example. It's commonly used in the production of animal feed. The N protein level is a key property and has a direct bearing on the cost of the material or the price you could sell it for. So specialized macroanalyzers for nitrogen-only determination are regularly used for this application, and all combustion products other than N2 are either separated, absorbed, or combined with a carrier gas, such as CO2 for a carrier gas. So the key thing here is that for soy meal, it has about 12% moisture content. So each 200 milligram sample produces 24 milligrams of water to absorb, and this can be a big challenge if you're just using a chemical desiccant. So how do we remove water? So recall that our gas stream after the combustion and reduction contains these CO2, N2, H2O, and SO2. For classic elemental analysis, where the sample sizes range from 1 to 10 milligrams, just a chemical desiccant, which we'll talk about later, can be used without any issues. However, for macro analysis sizes of 100, 500 milligrams, even 1,000 milligrams are not uncommon. For food or agricultural samples, this can produce a large amount of water vapor. So some analyzers will use a combination of pre-condensation or membrane drying, followed by fine drying with a chemical desiccant. So condensers cooled by either a Peltier system or just a fan with an ambient air can be used as a first stage. So in this case, it's just a open U-tube with a fan blowing on it is often a first stage of drying. Second stage drying can be used a membrane dryer, such as a product name is Nafion, which is very effective, and it either is used as a second stage or sometimes by themselves. The moist gas stream flows through the center of the membrane, which is selectively porous to moisture but not to our analyte gases, so they stay on the inside. And then there's a counter flow of gas going through the outside of the membrane tube, which wicks away the moisture. Generally, they do not dry sufficiently enough for the required analytical accuracy of elemental analysis, but they can get rid of a big bulk of the water, so which that is key and often are used. Which brings us to chemical desiccants. So there are two basic types of desiccants: adsorption desiccants and adsorption desiccants. So absorption is when the water is reacting chemically with the desiccant itself, versus adsorption, where the water vapor is held inside another material by a physical interaction. It's sort of in the maze of its internal surfaces. Silica gel, molecular sieves, calcium sulfate, which is the material of Dryrite, and SpongeBob would be examples of the adsorption process. Now, our ideal properties for a desiccant would be that to have sufficient moisture capacity to allow for a day or a shift of samples to be processed before it needs to be changed, for it to have a low vapor pressure, meaning that it really captures most of the water vapor that's going past it, such that traces of water do not interfere with the other analytes. It also needs to have good flow properties as well when it's dry, as well as when it's near water holding capacity, because all of our elemental analyzers are gas flow systems. If we disrupt the flow rate, we're disrupting the accuracy of the analyzer. And we also have to have it not reactive for other analytes, such as the N2CO2, SO2 of the sample. Ease of handling, that is easy to fill these tubes, easy to empty them, and they should be of a reasonable cost. So those are the goals of what we're looking for. So some examples of absorption desiccants are shown here. These are easy to use and have no shipping restrictions. Their vapor pressure levels are generally too high for most applications of elemental analysis. So Dryrite, silica gel, molecular sieves, again, they have high capacities, good flow rates, might have some interferences with sulfur and or CO2, but this moderate vapor pressure is an issue to use it at least by itself. So then we look onto the adsorption materials. Listed are some of the typical ones used in elemental analyzers. So magnesium perchlorate is regularly used in elemental analyzers. It's easy to handle and fill the drying tubes. Its main issue is that it can block flow when it is wet, and it is also can be difficult to remove from the drying tube because it can form a hard block. It does not come out easily. This, in general, is a hazmat for shipping material due to its oxidation properties. And the capacity is rated as moderate, okay? So this works very, very well for the classic elemental analyzers, but we start getting into the macro analyzers, that's when it becomes a bit problematic. So Desiccant is the name of a material which forms phosphoric acid. When wet, it's highly exothermic. In its pure form, it's seldom used because it's highly reactive. Merck, the chemical company, has produced this product called Desiccant, which is a phosphorus pentoxide coated on an inert support, which is basically it dilutes it. It makes it much easier to handle. Still requires gloves and a hood. It has a very low vapor pressure, so it's great for elemental analysis. It has high capacity, good flow when wet. So this has been a very good desiccant to use, especially for macro analyzers. However, it has been discontinued by Merck, and industry is very specialized. I think they just didn't see the economic reality to keep this going. So this is what drove us for looking for a new desiccant. I'll also mention the calcium chloride, seldom used for elemental analyzers. This is primarily due to its deliquescent properties, which means that it forms a liquid when it gets wet. And but due to the non-availability of secapent, we're looking to use this as part of a solution for these high-capacity desiccants that we're needing. So Elemental Microanalysis has developed a replacement for secapent using a hybrid concept. It uses the trade name we're calling this is DryZorber. Our part number is B1327. So it uses a combination of molecular sieves for its great capacity and flow property. It puts in some calcium chloride to be used to lower the final vapor pressure, but not too much to cause blockage when and if it liquefies. And we throw in some cobalt chloride added as a wet indicator, which will change color on exposure to the moisture. The one drawback here is this is not appropriate for sulfur determination, as the SO2 can absorb into the molecular sieve stage for tailing, and you'll get something less than full recovery. However, we do have, the slide will come up, we do have a DryZorber S, another material that can be used with sulfur. It is basically a magnesium perchlorate on an alumina support. We add calcium chloride for the color change. This can be appropriate for both carbon, nitrogen, hydrogen, as well as oxygen analysis. Well, not hydrogen. And it also does not need a shipping surcharge because the magnesium perchlorate is diluted on the alumina, and it qualifies under the accepted quantity limitation for shipping. However, this does have a lower capacity than our regular DryZorber. So if you're using sulfur with macro analyzers, this would be the go-to material. If you're only doing carbon nitrogen, then the other form of DryZorber would be the choice. And again, just for our regular classical elemental analysis with the small sample size, 1 to 5 milligrams, 10 milligrams or so, magnesium perchlorate is a very excellent indicator to use. We make it in many different forms, whether it's flakes, granular, indicating, non-indicating, several different pack sizes, etc. These are shipping hazmats, except if you get the 25-gram size or less, this will also be able to ship without the surcharges. Generally, the flakes have a little lower capacity, but have better flow properties when wet. Those still can clog up. Granular has higher capacity, but if you get it overly wet, it can block the gas flow and so forth. And just to remind everybody that EA Consumables is the U.S. supplier of elemental microanalysis products, and we are a one-stop shop for all elemental analyzer users. Our web shop, eaconsumables.com, many, 200 or plus types of tin silver foils for encapsulation, your quartz tubes for the furnace tubes, specialized IRMS chemical supplies, furnace and absorption reagents, standards, O-rings, and parts. And as a bonus, we do ship candy with every single order. So thank you very much for attending this webinar. I'd be happy to answer questions.
Thank you very much, Scott. At this time, we are going to move into our question and answer session. So again, if you joined us late, you can send in your questions by typing them into the Q&A box that's located on the right-hand side of your screen. I'd also like to remind you that you can look under the handout tab on the right-hand side of your screen for more information about this presentation. So now we're going to take our first question from the audience, and that is, what impact does particle size have on the lifetime of the desiccant?
Again, for this would probably mostly be for the magnesium perchlorate. So the particle size, the smaller the particle size, the higher the capacity, the water holding capacity of the desiccant. However, these smaller particle size packings can, when they get very wet, start inhibiting the gas flow through the analyzer, which will cause big problems. So the flakier, the larger particle size or flake size have a bit lower capacity but better flow properties.
Okay, great. So we have another question from the audience, and that is, do desiccants with indicators cause issues when doing IRMS work?
A very good question. So there are a lot of folks that feel that the indicators may cause some shifts when you're doing nitrogen or carbon isotope work with elemental analyzers as the front end to a isotope ratio mass spectrometer. However, when I was with Elementar, which made the isoprime range of IRMS systems, we did a lot of work with desiccants with and without indicators, and never could find a time when the presence of the indicator caused problems. It's kind of like a old wives' tale sort of thing. When you're having trouble with your analysis, you're changing a lot of things, and sometimes you fix it. And one of the things that you also changed was using a non-indicating desiccant. Maybe that's where that came from. But in my experience, doing tests, etc., the indicators do not cause any problems.
Great, thank you. So I have another audience question here, and they were wondering if you could talk about other symptoms of desiccants that are in need of changing. So they also mentioned, is carbon peaks more effective than nitrogen peaks or vice versa?
Well, when water gets through the system, it causes all sorts of problems almost everywhere. So, if you're having trouble with your analysis, strange results, etc., it's always good, number one, to take a look at your desiccant columns and see if they are healthy or are needing to be replaced. Desiccants, it's not that expensive, so replacing it may be a first step in troubleshooting some of these things. But it's hard to, water just gets in there, it can get into your column, it can pop out in all different areas, so it causes big problems.
Great, thank you. So I have another question here. How do you tell if a non-indicating desiccant needs to be replaced?
Usually you take a look at it, and even though it's all white and doesn't change color, you can typically tell there's been a physical change in at least the absorbing type desiccants, such as magnesium perchlorate. So you can look at it and see that it looks different than the top edge that is more dry, so you can kind of see the line. In the case of a molecular sieve and stuff like that, you really can't tell. So that's why with that type of stage and a desiccant, we do put something else that changes color.
Great, thank you. My next question is, are there ways to make it easier to remove wet magnesium perchlorate desiccant?
Yeah, so what some people do is they'll take the magnesium perchlorate and mix it with a 1-to-1 ratio of quartz chips to kind of give to break up the granulars a little bit and fill the tube in that way. That would be the one way. The other is to change it way before it gets overly wet. If it gets real wet, it can form just a block, and that can be a real trouble to get out of your glass tubes.
Great, so I have another question, and that is, Phosphorus pentoxide is still available, so how is it different from Desiccant, and can it be used instead of Desiccant?
Well, technically, yes, you can, but pure phosphorus pentoxide is really, really nasty stuff to handle. Um, if you were to try to use it again, you would mix this with quartz chips would be your only chance of doing something to get it in and out because it is so reactive. It gets very hot. It can it will absorb a lot of moisture right from the atmosphere, etc. It's nasty stuff, and in most cases, I would say it's not a practical use in a routine laboratory unless you really, really need the very low vapor pressure that phosphorus pentoxide uses. It's unfortunate that the Desiccant's no longer available. That was a nice compromise for everything, but that's the way it goes. And but we think we have a very nice replacement in the dry sorber material.
Great, thank you. So that brings us to the end of today's webinar. Just a reminder that this webinar will be available on demand shortly following this live presentation. So please watch your email for a message from Lab Manager once this video is available. On behalf of Lab Manager, I'd like to thank Scott Hughes, PhD, for all the hard work he put into this presentation, and I'd like to thank all of you for taking time out of your busy schedules to join us. Once again, thank you to our sponsor, EA Consumables. Their support allows Lab Manager to keep these webinars free of charge for our readers. For more information on all our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you and have a great day.